Astronomers have found new evidence against the standard model of cosmology. They have discovered a theory that could replace dark matter and ultimately solve one of the biggest mysteries in astronomy. The new theory is called AQUAL and implies that dark matter may not exist at all. The researchers tweaked Newtonian gravity to fit the observations of galaxy rotation curves. Besides correcting a possible 90-year-old mistake, their results may open new windows to the fundamental understanding of gravity itself. But what happened 90 years ago that changed the course of cosmology? Why are physicists developing an alternative theory of gravity? Finally, and most importantly, how can the new idea lead us to a better understanding of the universe? Dark matter is one of the most important entities in the standard model of cosmology. It is a hypothetical form of matter believed to make up 27% of the observable universe. The problem is that dark matter does not interact with electromagnetic radiation, making it difficult to detect directly. Instead, its existence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Even the standard model of particle physics doesn't contain any elementary particle representing dark matter. Although scientists are pretty confident that dark matter exists, they are still trying to understand its properties and behavior. Their goal is to develop a definitive theory that explains its nature. To understand AQUAL, it's important to learn how dark matter even came into the picture. It was in 1933 when Swiss astronomer Fritz Zwicky noticed something was missing in the universe. He studied galaxy clusters and concluded that the observed mass of matter was not accounting for the total mass of the galaxy cluster found based on the motion of the galaxies held together by the gravitational force. He discovered this discrepancy in the Coma cluster. Zwicky first calculated the mass of the Coma cluster by studying the galaxies at its edge. He then compared it with the mass based on the brightness and the number of galaxies in the cluster. The two values didn't match. As a result, he obtained evidence for an unseen type of matter, which he called dark matter. Supporting his study came American astronomer Vera Rubin's analysis of galaxy rotation curves. A galaxy rotation curve is a graph of the orbital speeds of visible stars or gas in the galaxy versus their radial distance from the center. A rotation curve for our solar system looks like this. The average rotational velocity of planets in their orbits around the Sun decreases as their average distance from the Sun increases. So, the farther a planet lies from the Sun, the slower it goes around it. Mathematically, their orbital speeds are inversely proportional to the square root of the radial distance from the Sun. However, Rubin and her colleague Kent Ford found that the stars in the galaxies did not obey such rules. In fact, it's the opposite. Almost all stars in the galaxies revolve around the center at increasing speed as the distance increases. They noticed that the outer regions of these galaxies were rotating at the same or increasing speed as the inner regions, which was unexpected based on the known distribution of visible matter in the galaxies. This seemed only possible if there was a significant amount of unseen matter in the galaxies. Just like Zwicky, they referred to it as dark matter. With time, more evidence in favor of dark matter poured in. First, in the 1980s, the observation of gravitational lensing of background objects by galaxy clusters supported the presence of dark matter. Then, in the 1990s, measurements of the cosmic microwave background and the large-scale structure formation of the universe hinted that something like dark matter must exist in the universe. Specifically, these observations showed that the universe is much more clumpy and filamentous than one would expect if it were composed of visible matter alone. Although the concept of dark matter is strongly established in modern cosmology, there's a big problem. Scientists are not sure what comprises dark matter. As stated earlier, there's no elementary particle in the standard model that makes up dark matter. The hunt for such particles is still going on. Several candidates for dark matter have been proposed, including weakly interacting massive particles, massive compact halo objects, exons, and sterile neutrinos. Scientists continue to search for dark matter particles at the Large Hadron Collider. Through experiments such as CREST, LUX, Zeppelin, the Exeon Dark Matter Experiment, the Xenon Dark Matter Experiment, and the dark matter maps from the Dark Energy Survey. But so far, all these experiments have returned empty-handed. So naturally, one would think, what if there is no dark matter at all? What if this is a flaw in our understanding of gravity itself? Many teams of researchers are on a quest to find alternatives to dark matter. One such alternative is called the Modified Newtonian Dynamics, or MOND. It involves the modification of Newtonian gravity to apply to the galaxy rotation curves. Since Newton's laws are highly tested and valid for high acceleration systems like the solar system, MOND, proposed by Mordechai Milgrom in 1983, took a step towards a modified gravitational force law for an extremely low acceleration environment. This theory assumes a threshold acceleration below which there is a transition from Newtonian dynamics to MOND regimes. Based on this idea, a generalized theory was constructed by Milgrom and Jacob Bekenstein in 1984. It's called AQUAL, which stands for A quadratic Lagrangian. This theory modified Newtonian gravity by changing the classical Lagrangian to a Lagrangian involving a general function and the threshold acceleration term. The currently accepted cosmology model is the lambda cold dark matter model, or the LCDM model. Let's understand how it's different from the AQUAL hypothesis. There are two important parts of every galaxy's rotation curve: the inner one, which is a rising curve, and the outer one, which is slightly increasing or almost saturated. These parts correspond to the motion of stars in the inner and outer regions of the galaxies. Since the LCDM model attributes the galaxy rotation curves to the presence of dark matter, the distribution of matter should account for both the inner and outer portions of the rotation curve. On the other hand, AQUAL asserts that the transition caused by the galaxy dynamics accounts for the difference between the inner and outer portion of the rotation curve. The small kink in the curve is due to the slight change in the velocity distribution between the inner and outer stellar motions. That's how the LCDM and AQUAL models differ. Now this is where the new study by K.H. Che comes in. It chiefly focuses on how differently modified gravity and dark matter explain the inner and outer proportions of the rotation curves. He studied 152 galaxies observed in the Spitzer photometry and accurate rotation curves, or the SPARC database. He aimed to determine the theoretical possibilities of distinguishing dark matter and modified gravity. To do so, Che studied the statistical relation between the observed centripetal acceleration of particles in motion and the expected Newtonian acceleration from the distribution of baryonic matter in the galaxies. The baryonic matter corresponds to stars and dust. The dark matter model showed a larger scatter than the SPARC data. The SPARC data of 152 galaxies considered in this paper supported AQUAL better than the LCDM model. He noticed that only under the application of cosmic mean external field did the AQUAL modified gravity predict correctly both inner and the outer parts of the rotation curves. This study has presented a detailed analysis of AQUAL and its potential to provide new insights into the nature of gravity. Although the results are exciting, AQUAL has its own drawbacks, as it cannot thoroughly explain the observed gravitational lensing by galaxies. But this study is a step towards understanding the theory's pros. It's possible that just by tweaking Newtonian gravity, we can solve one of the biggest puzzles in cosmology and astrophysics. Recently, scientists simulated a black hole in a lab that mysteriously started glowing. This experiment has enabled them to have a deeper understanding of Hawking radiation. You can watch this episode to learn more about it. Also, make sure to subscribe to our channel so that you don't miss any future videos.